All right, so I want to talk about a particularly simple yet important application of what we just proved, and that is as follows. So let's say we have a measurable function, extended real valued. Okay. Let f plus be the positive part of f. So it's a maximum of f of x 0. So if f of x is, well, we'll see what's exactly going on in a moment. Let's say f minus is the negative part, which is a maximum of minus f of x 0. Okay. So, yeah, so the maximum of these two functions is measurable. And you can check that minus f of x is also a measurable function, basically by definition, essentially, if f of x is a measurable function. So the maximum of these two is also measurable. So these are two measurable functions. And I claim that f of x is f plus minus f minus of x. And I also claim that neither of these can simultaneously be non-zero. So I'm perfectly fine subtracting these two functions. If one is not 0, then the other has to be 0. Let's prove that. And like a lot of stuff in this course, you just have to unravel this. There's not much more to it than that. Let's look at the case, there's two cases, f of x equals 0. So if f of x is less than or equal to 0, then f of x equals the max. Well, this is less than or equal to 0, so 0 is the maximum. Sorry, f plus. F minus is a maximum of minus f of x 0. Well, minus f of x is bigger or equal to 0. So the maximum of this is obviously minus f of x. Okay. So in this case, f of x is, well, 0 minus f of x. So f of x could be minus infinity. There's no problem here. But in this case, f plus is 0, so no ambiguity whatsoever. There's no issue with defining this. Okay. On the other hand, if f of x is bigger than 0, then, right, so f plus of x is going to be obviously f of x. On the other hand, f minus is going to be 0, because minus f of x is negative. Yeah, sorry, this is negative. So the maximum of this is 0. So f of x equals, well, f of x plus 0 is going to be f plus of x minus f minus of x. Right? And again, here, in this case, f minus is 0. So always one of these, f plus or f minus, is going to be 0. Okay, and right. So in general, f plus is f of x when f of x is bigger than 0, and f minus is minus f of x when f of x is less than or equal to 0, and that's why we call it the positive and the negative part of f. It's, you know, particularly for the negative part, we're just making it positive by, you know, by saying it's minus f of x when f of x is negative. So what's the point here? The point here is particularly when we define Lebesgue integration, you know, this new integration process based on everything we're doing, we only need to define the integral of a non-negative function, because then we can just define the integral of a general function to be, well, the integral of f plus minus the integral of f minus. Assuming we're not having a minus, you know, an infinity minus infinity type situation going on. But that's really the main point. And the key is that both of these are measurable. So, yeah. Okay, so last but not least, I want to talk about pointwise limits of measurable functions. Okay. Remember I said that measurable functions, the idea is that basically a function that we're going to be able to integrate, more or less. And certainly you'll remember that pointwise limits of Riemann integrable functions need not be Riemann integrable. And, you know, you don't have to search far and wide. You can just say, let's say, take fn of x to be, so let's say enumerate the rationals between 0 and 1, and let's say this is 1 if x is in Rn, let's do K, sorry about that. 0 if x is not. So x is 0 to 1, take away so Fn is Riemann integrable. It's continuous except for a finite number of points. So Fn is Riemann integrable. That's R for Riemann integrable on 0 to 1. The limit function is not, and this is that famous Dirichlet function. That's 1 if x is rational in 0 to 1. 0 if x is irrational in 0 to 1. And hopefully you did this in 511, that this is not, or whatever course you took, basic analysis, this is not Riemann integrable on 0 to 1. And if you want a review of the Riemann integral, just go to my video and watch it. I probably talk about this maybe in slightly different notation, but right, so this is in stark contrast to what I'm going to prove right now, where I'm claiming that pointwise limits of measurable functions is measurable. Okay, so let's say, just like before, each Fn I just want to also say one nice, useful benefit of a new integration process that will generalize the Riemann integral on an interval, in the sense that the two are the same if we have a Riemann integrable function on an interval, is that we can integrate, we're going to be able to integrate over basically any measurable set whatsoever. So we're not restricted to intervals like we are in the Riemann integral. Okay. There's a lot of reasons why the Riemann integral is not so useful in practice. So assume each one of these is measurable. Again, E, we assume for the millionth time is measurable. So I really don't need a new definition, or I don't really even need to define at this point what Fn converges to F almost everywhere means. I guess I kind of do. Well, it's if the obvious thing is true, and in words we say Fn converges to F pointwise almost everywhere to almost everywhere on E. Or just Fn converges to F almost everywhere on E. Probably other similar wording. So this, we say this is true if kind of the obvious thing is true, and at this point we don't know if this set is measurable or not. So let's use outer measure, and not that it matters because we're assuming it's 0. But yeah, this set here is 0, has measure 0. Set of all x where Fn of x does not pointwise converge to F of x. Okay, so we're saying that pointwise we have convergence except possibly at a set of measure 0. So the set where we don't have pointwise convergence has measure 0, and hence it's very consistent with our previous usage of almost everywhere. Fn converges to F almost everywhere means the set of x where we don't have pointwise convergence has measure 0. Right. Okay, so we have the following proposition. So if this is true, also a lot of times we say Fn converges to F almost everywhere on E. It's kind of a quick, lazy way of writing this. These all mean the same thing. It means this here. Well, really means this. But yeah. I particularly like this terminology because it's nice and quick. Yeah, so if each Fn is measurable, then F is measurable on E. Okay. And maybe to clarify a little bit, so here let's assume F is some measurable, maybe this is probably obvious, but let's assume F is just some function, not necessarily measurable. Right? Let's assume f is just some extended real valued function on E. So implicit here is that f is some real valued, some extended real valued function on E. We don't know if it's measurable or not. The claim is that f is measurable. All right, so what's the proof? Well, as we'll do many times, well, I guess we're not going to do it too many times more because the semester's almost over, but if you go in my future videos, we'll have to do this quite a few times. The first thing to do is excise a set of measures 0 out. It's kind of a pain because we're going to have to do this over and over and over again, but anyway. Right, so what do we need to do? So first of all, let me give this a name. I don't know what to call this. Let's call this set E. Okay, so what do we yeah, and probably the trickiest part of this proof, as before, is figuring out which of the 4 conditions for measurability to check. And it turns out this is the one that's most convenient. So we need to show this is true for any C real. Okay, right. So let's just excise a set of measure 0. So just kind of trivially write this as inverse image now, if it's not clear why this is annoying, I'll make that clear in a second. Excising a set of measure 0. Sorry, this is a terrible choice. Let's call it E prime because E is my domain for all of these functions. So do not call this E. That would not be a good idea. So let's say we're on E prime. Well, let's write as a disjoint union of we're either on E prime or we're not on E prime. So it's the inverse image intersect E, take away E prime. Okay, so let's say this set here is A, and let's say this set here is B, for lack of anything better to call it. I guess I haven't used purple in a while. Right, so obviously the measure of A is 0, or outer measure of A is 0. Sorry. So we're assuming that this set has measure 0. Okay. So this is a subset, it has measure 0. So obviously this is measurable. So you really get a lot of mileage out of that almost trivial fact that sets of measure 0 are measurable. Okay, so the point here is we can assume that we're dealing with just points where Fn converges to F. Fn of x converges to f of x. Right. So we have that this is measurable i.e. this is an M, if this set here sorry about that. Is measurable. Yeah, I'm getting sick of this tilde notation, so yeah, really getting sick of it. Okay, so right. So the point here is that, yeah, as I said, we can assume Fn of x converges to f of x, and we want to look at, among all those x, the set f of x is less than c. And we have to somehow relate that to the fn's. And the way we're going to do that is following. So I claim that if x is an x take away e prime, maybe a little clearer to say, if this is true, then I claim f of x is less than c. And if you did something other than less than c, this would be a little tricky. But you might be able to do bigger than c. But anyway. So I claim this is true if and only if there exists two natural numbers n k where fj of x is less than c minus 1 over n for all j bigger or equal to k. Well, why is this true? There's not much to it. Tricky part is just thinking about writing, just coming up with this. That would be, that's a bit tricky. But once you have this, you should definitely be able to prove it pretty easily at this point. Right, so why is this true? Now, let's suppose f of x is less than c. So let's look at two cases. Let's look at f of x is minus infinity. There's no case f of x is positive infinity, because we're assuming f of x is less than a real number c, so it can't be positive infinity. Okay, this is the case, well, in the really Calc 1 even sense, or Calc 2 sense, but basic analysis sense, this limit here converges to minus infinity. It's, yeah, I mean, technically it doesn't converge, but it's, anyway, whatever. So all you need to do is pick, right. One second. Yeah, sorry about that. So for any natural number n whatsoever, there exists k where fj of x is less than c minus, kind of obvious here, but for j bigger or equal to k. I mean, yeah, fj is eventually less than anything. So pick any natural number n whatsoever. Right. Okay, so the other case is f of x is real valued. So we have like a genuinely convergent limit. Okay. So we're assuming that f of x is less than c. So pick small enough n. F of x, and you can always do this, is less than c minus 2 over n. Yeah, we're assuming this here. I guess I'll do, I don't know. So we're assuming this. So that's what allows me to do this. That's, you know, don't want to say more about that. All right, so now let's do epsilon delta. So let's say epsilon is 1 over n. And pick k, natural number k, where k bigger or equal to j implies that I meant j is bigger or equal to k. Fj of x minus f of x is less than epsilon. Just convergence of fj of x to f of x, nothing. So in particular, we have kind of trivially then fj of x is less than f of x plus epsilon is 1 over n. This is less than c minus 2 over n plus 1 over n, and that equals c minus 1 over n for small enough n. Okay, so conversely, so we just proved half of the statement. Got to prove the other half. So now let's assume this here in light blue is true. Let's assume this is true. So conversely, if there exists n and k where fj of x is less than c minus 1 over n for all j bigger or equal to k, well then fj of x, f of x is a limit and so that's less than or equal to c minus 1 over n, because, you know, obviously, if this is true, then the limit is less than or equal to c minus 1 over n. And that's less than c. Right. So, yeah, not a lot to that. So that takes care of this proof. All right, so what's the point? And again, I just want to just emphasize, I am away from the set. Yeah, if x is in here, then I'm away from the set where we do not have pointwise convergence. So we do have, for x in this set, fj of x pointwise converges to f of x. So there's no issue about that. We've removed the bad set of measure 0. But it's measure 0, so who cares? Who the hell cares? Okay, so finally, what does this allow me to do? Well, this set here, the inverse image of minus infinity to c, intersect E take away this bad set of measure 0, where we don't have pointwise convergence. Well, kind of the usual standard translate into unions and intersections. So there exists means unions for all means intersections. Yeah, so this is going to be equal to, and yeah, this is all in the book, so I would give this for homework probably if it wasn't, but it is. So it's the intersection of whoops. Yeah, so maybe I'll put this whole thing in light blue now. So we're just looking at, now that we're done with intersections and unions, this has to be true. X has to be in the inverse image of minus infinity to c minus 1 over n. And we know this is measurable, because each one of these is measurable. Right. 1 second. Yeah, sorry about that. Squeeze this in here. Yeah, and this only works if we're in E take away E prime. So, right. So, yeah, E is measurable. We excise a set of measure 0. That's still measurable. So everything is measurable. Fj is a measurable function, so this is measurable. So it's the countable intersection. The countable intersection is measurable. So countable union of measurable sets is measurable, et cetera, et cetera. So that's measurable. Okay, so that basically takes care of the basics of measurable functions. Next, we're going to talk about kind of build on what I mentioned with simple functions. I'm going to talk about adding and putting together characteristic functions to form what are called simple functions, because, no pun intended, they're very simple. That's the whole point. And then we'll get into much deeper results like Egorov's theorem and Lucen's theorem and Pizza's extension theorem. Okay, so next we need to talk about simple functions, and then we'll prove that in some sense every measurable function is almost a simple function. All right, so what is a simple function? Well, in some sense, it's just a really simple function. No pun intended, it really is. So we have var phi simple if two things are true. Well, it's measurable. Well, three things. It's real valued, measurable, and the key here is that the image is finite. It only takes on finitely many values. Okay. So let's prove the following little proposition here, which tells us exactly how to write a simple function out. Whenever I say if var phi is simple, there's an underlying measurable set E that is its domain. So right, so there exists pairwise disjoint and measurable EKs. Oops, sorry, that. And real numbers, CK. Where this function here is just given by some, just a linear combination of characteristic functions. All right. Yeah, so every simple function is just the linear combination of characteristic functions. Right. Yeah, and the converse is true, though we don't really need it. Any linear combination of characteristic functions is itself a simple function on the union of the underlying sets for your characteristic functions, because any such function is measurable, and obviously the image is finite. All right, so what's the proof? Proof is pretty obvious. Okay. Yeah, so the proof is just, let's say 5e, the image is just C1 through Cn. And let's assume that these are all distinct. Right. And let's say EK is the inverse image of the singleton CK. Right. So I claim that this basically does it. Okay. So phi is measurable. Okay. So this here is measurable. Because we know the inverse, we proved that the inverse image of a singleton is measurable. So no issue there. So if X is an E, well, then phi of X, var phi of X rather, has to be one of these. Okay, so obviously that means X is in the inverse image, and here K0 is between 1 and n. It's an integer. Yeah, so that means X is in this inverse image. All right, so what does this mean? This means that this sum here just basically break it up into two sums. Kind of obvious probably that this is going to give you CK0, but if it's not, then let's just see why that's true. I'm not going to try and squeeze it. Okay, well, what's this going to be equal to? X is an EK, so this here is going to be equal to 1. So this whole thing here, obviously, is just CK0. So this is CK0. Well, each one of these is going to be 0. And the reason why is pretty easy. Phi of x is not CK because it's CK0, and we're picking all these distinct. So that means x is not in the inverse image of the singleton CK, which is EK. So each one of these is 0. Right? So, yeah, this is equal to CK. It's phi of x, and we're done. We picked an arbitrary x. This sum here for arbitrary x and e gave us 5x. So not a terribly deep proof, but right. So yeah, let me state a very useful but pretty trivial proposition. So if I have two simple functions, f and g, and they're both simple, well, I'll state it like this. Alpha f plus beta g, let's say alpha and beta are scalars. Then this is simple. I mean, the proof, there's really not a whole lot to the proof. Clearly, this is finite. And this is measurable. Because we're adding, well, taking a linear combination of two measurable real-valued functions. Right. So, yeah, useful property that linear combination of simple functions is simple. So I want to make one comment, and this would be worthwhile to remember this. So this here this is going to be called the canonical representation canonical meaning, the natural representation. There are other ways to write a simple function in terms of a linear combination of characteristic functions. This is not the only one. You can certainly combine. Sets ek if you really want to, or even just rather break up ek into two pieces and have repeats. There's other ways to do this, but this is the most natural. This is the most natural way. So what do I mean by this? I mean ek being the inverse image of each of the distinct values that phi takes on. Okay? So the canonical representation is just write out the distinct values that phi takes on, take the inverse image, and then write the function like this. So, right, so for example, if you had something like, I don't know, let's say this is E, and let's say we had a step function like this here, or a simple function rather. So let's say this is C1, C2, C3, not exactly lined up, but it's all right. Yeah, so this would be, let's say, E1. Whoops, sorry about that. I meant to include this here. So let's say this whole thing, this interval is E. E2. Sorry, this would be E3. Now, of course, we can order the C's differently. It doesn't really matter how we order them. And sorry, this would be not starting this video off too well, but this would be E1. If I say this is C1, if this is C2, this would be E2. If this is C3, this would be E3. Okay, yeah. And of course, the, writing E, or this actually partitions E, saying that the image is these C's. Okay. This definitely partitions E. And the C's could also be 0. There's no problem there. If, let's say, instead, I had something like, let's say this here was C4, just y equals 0. And let's say, E is from this point to this point. And if the simple function is just 0 here, that's okay. No problem there. This would be, so let's say it's open, closed here. Then this would just be E4. So no issue with any of the C's being 0. Okay. All right, enough of that. All right, so let's prove something not very difficult, but extremely useful. And that is as follows. Let's say f is anything bounded and measurable. Right. So I claim that for any epsilon bigger than 0, there exists simple functions let's say, just using the book's notation, var-phi, guess this is psi, whatever. Anyway, there exists for every epsilon, there exists 2 simple functions where the following is true. Well, f is sandwiched between these 2 simple functions. Oops. Sorry about that. For any x and e. 2, these simple functions are very close to each other uniformly on E. So for any x in E, this is true. I should just, I don't think there's any confusion, but in case there is. And last but not least, both are bigger or equal to 0, they're non-negative on E if F is non-negative on E. So one thing I want to emphasize before I prove this is that in this picture here, this simple function looks very nice, but graphically, your simple function might look horrendous. That's okay. So for example, let's say let's say E is the whole real line, and let's say 5x is a Dirichlet function. That's a perfectly nice, simple, nice, good, simple function. So it's 1, x is rational, 0, x is irrational. Okay. So the canonical representation here is pretty obvious. It's just simply, it's going to be 1 or right, so it's going to be just the characteristic function of the rationals. So it is a bit sometimes silly to write out the 0 part for your canonical representation, but so yeah, you don't have to really do that. This is really just a characteristic function of the rationals here. So yeah, the point here is that you definitely can't draw this, but certainly the rationals are measurable, obviously, because it has measure 0, so no issue there. But yeah, anyway. All right. All right, so let me prove this. Yeah, and the proof, I'll just quickly draw the proof idea. The proof idea is not difficult. Let's say we have something like, I don't know, some nice function here, here to here. Let me draw it a little higher. So yeah, we have something like this here. The idea is just to basically partition the range in such a way, let's put that here, that each partition interval has width epsilon. Yeah, and we can do one of two things. I'll do var phi epsilon. If we have x is between these two partition points, we just say var phi epsilon is the lower one. So that it's, right, so yeah, and we form simple functions in that way, basically. And that's really all there is to it, really. Et cetera, et cetera. Still kind of a pain to draw, but you get the idea here. Yeah, so this is going to be, let's say, green. So let's just order this E1. Maybe I won't do green here. I'll do purple, as good as anything. I'll just do E1 and E2. But anyway, you should get the idea here that we're doing. So the union of these are E2. I'll maybe do one more. I'll do yellow. And because we're partitioning in this way, we're certainly going to have, by definition, really, var phi epsilon being within, well, we'll have, if we do, so I'm doing this, I mean, we can, this is kind of akin to upper and lower Riemann sums. If I did, if I basically did this for the maximum of my function on the interval, then I would get this one here. And you can kind of imagine if I did that, because the partition width is epsilon, we would have two simple functions that differ by at most epsilon. So let's make this very precise. All right, so yeah, and I would draw this here. Again, this is very much akin to doing upper. It's basically the same, exact same idea as upper and lower Riemann sums, except we're partitioning the y-axis. we're not taking volume here, but we're still basically looking at the max and the min on each basically interval. All right, so what's the proof? Yeah, do exactly what I'm saying. Now obviously, we're dealing with a general measurable function. So this might look, God knows what f looks like. It's just a very abstract general measurable function. But still the idea is the same. Let's say f is a bounded function. So certainly it is a subset of some half-closed, half-open intervals c to d. So in particular, if f is non-negative on E, then we can set C to be 0. And we do. If f is never negative, then the image is contained in 0 to D for some large D. Okay, so here, this is my D here, and this is my C in this picture. I mean, strictly speaking, I have to make it a tiny, teensy-weensy bit lower, but anyway. Well, I guess technically I have C, I have to make D technically a teensy-weensy bit higher, but I'm just doing half open, half closed to make things a little technically easier. But intuitively, this is my D and this is my C, right? Okay, so, right. Break this, do a standard partition of my interval like you do for Riemann sums. For n bigger than 1 over epsilon, let change in y be d minus c over n. So this here, more precisely, so let's pretend that these are all even. Yeah, this is change in y, it's an epsilon, d minus c over n. Okay, so that's enough of the picture. Yeah, hopefully that picture is helpful. If not, I apologize for wasting everyone's time. Feel free to skip over it, obviously. It's kind of the beauty of these videos. Yeah, so for j equals 0 all the way up to n, just do the same thing as you do for Riemann sums. Yj is c plus delta y. So this is y0, y1, y2, y3, y4, y5, y6. Here, big N would be 6. Got 6 of these, 1, 2, 3, 4, 5, 6. So let's see, example C3. I'll just draw. This would be C5, etc., etc. All right. Right. So what do we do? So just notice, of course, that y0 is c. Yn, well, I should say, for an integer j between 0 and n. So plug in n, you could just check trivially, you get d. It's just c plus d minus c is d. Right? So let's say, keep life a little simpler, ik is y maybe I'll do k here. So let's say ik is just yk minus 1 to yk. I should mention we don't exactly have to have d being the supremum of the image of the function. D could be larger, it's no problem. All I really need is this here. I really just need this. Okay? And also c doesn't have to be the infimum of the image. All I care about is this. Okay? Though if f is non-negative, then I do emphatically want to and will and am setting c to be 0. I'm allowed to do that, and I do want to do that. All right. Yeah. Right. So for k between 1 and n, ik be this. All right, and do like we did basically before, similar to what we did before. Not exactly. Let's say ek, well, yeah, do what I'm doing in this picture. Ek is the inverse image of each of these intervals. Okay. And do what I did in the picture. Let's say var phi epsilon is this simple function here. Where the value on ek is going to be the left endpoint of my interval. Sorry. All right, and do the same thing. And again, probably it's not a bad idea in this example to draw this one here. This is going to be basically the same thing, except the value on each ek is the right endpoint of my interval. All right, so let's check everything here. And just like a lot of proofs with simple functions, it's just unraveling stuff. I mean, there's really not a whole hell of a lot to this here right now. Let's check one. So let's say x is an e. So let's say ck0 yeah, let's say ck0, let's just say, 1 second, I won't do that. No need to do that, sorry about that. Let's just say C, I guess I don't even need to do that. But let's just say, I don't even need to call this anything, but let's just say for simplicity, C is f of x. Okay. So the IKs obviously partition C to D, which is the point in doing a half closed, half open. It is strictly a partition. So f of x is in, well, it's in C to D. So let's C equals f of x is in IK for some interval IK. For k an integer between 1 and n. Again, the point is that the IKs partition C to D. F of x is in C to D, so f of x is in some IK, right? Okay, so what does this mean? That means x is in, f of x is in IK, so x is in the inverse image of IK is EK. Okay. So because IKs partition C to D, certainly the EKs are disjoint. There is clearly no x where f of x is in IK and IK prime for k not equal to k prime. That's just impossible. You can't have f of x being in two of these disjoint intervals. I mean, that doesn't make any sense. F of x is f of x. It's can't be two different elements, right? And there's nothing common between the IKs. So yeah, so with that. All right, so that tells us what this here is. Well, just a reminder, this is going to be k equals 1 to n of yk minus 1, characteristic function of ek. This is not the best. So let's put a 0 here. That, yeah, everything else is 0 because x is not in any of the other EKs. And when k equals k0, well, characteristic function is 1. So we get this here. And similarly, this is going to just be equal to, you can check, yk0. Okay. Right. So what does this tell me? So C is in IK0. So what does that mean? That means that yk0 minus 1, move this over a bit. Right, so this says that yk0 minus 1 is less than or equal to C is less than yk0. And again, this is nothing more than saying C is in IK0 is yk0 minus 1 to yk0. Okay, so we're done with 1. Why? Because this is what this is. This is what psi of x is. And this is what f of x is. Okay? So f of x is sandwiched between both of these. This is strictly less than, f of x is strictly less than this, but we don't care at all. Yeah. We just want less than or equal to. So that takes care of 1. 2, not all that much for 2. So just literally, let's say, do the same thing, x and 1 was picked arbitrarily, so use the same notation here for 2 as we did with 1. This was equal to yk0 minus yk0 minus 1. And by definition, this has length 1 over n, because we're just picking my intervals to have width delta y, well, d minus c over n. So actually, sorry, I should really have made this 1 second. Yeah, I should have made this d minus c over epsilon. So d minus c over n has d minus c over n is less than epsilon. Right. So each one of these has length delta y. So this equals, delta y, which is d minus c over n. And that's less than epsilon. All right, so 3, yeah, there's really not much to 3. If f is bigger or equal to 0, then c we set to be equal to 0. So all the y's, the yk's, are bigger or equal to 0. So we're done. So by definition, both of these are non-negative. All right, so that takes care of proof